Here's a quick video on how to use Cyscope to test your Schmitt trigger. So if everything's working correctly after plugging in the Schmitt trigger, starting Cyscope, all of that, we should see this. The input is at 0 and the output is as high as it can go, which in this setup is 4.74 volts. So if we want to see the Schmitt trigger in action, it's best to use a triangle wave and bring our amplitude up to 100%. And so you can see that it's for when the voltage is above a certain value, the output is 0 or close to 0. And when it's above a certain value, the output is high. If you notice, though, that the trip point here is not the same as the trip point there. So if you want to see that, you can go to XY mode, and basically the lower axis is V in and the Y axis is V out, and it will follow a different path from high down to low than if you're low and you go to high. And that's a bistable state, and that's what all the stochastic resonance for this circuit is based on. So just looking at the volts per division, right? Normally the x-axis is time, but because we're doing XY mode, 1 volt per division, 1 volt per division, it's kind of looking like it's half a volt, right? I can try to get a better estimate than that. I'll just turn off XY mode. And I need to zoom in on the voltage axis. So now I could kind of do it from here. By just counting up the divisions, 1, 2, 3, 4, 4.5, and then over here, 1, 2, 3. I can't do it like that. So I'm going to just take the left mouse button and drag the letter down to the lowest point possible, and I'll drive that down to the lowest point possible. Right, zoom in there, and now I should be able to count up divisions. 1, 2, 3, 4. It's, around 4.5, right? 4.5 divisions times 500 millivolts is 2.25 volts for the trip from low to high. And then here we have 1, 2, 3, 4, 5.5. Right, which gives us 2.75. The thing is based on these estimates, I still get about half, right? I could try to zoom in more. Oops. Let's see. But unfortunately, I can't really see where they intersect, and I'm going to keep B there. I'm going to drag A down, but you see I can't really tell where 0 is. So that's really as good as I can get. So I'm not going to bother. Anyway, let's put them back to where they were. Okay. Oops. 1 volt. 1 volt. So a lot of times Schmitt triggers are used to clean up noise, and I'm just going to click on noise. All right. And that's a little bit hard to see, so I'm just going to zoom in time, and it's not repeating because it's noise, but what you can see is that, it's taking this noisy signal, and here, let me see if I can even slow it down a little bit and put the noise more in the middle. That's better. So that's the noise, and what it's doing is it's cleaning it up and turning it into output highs or output lows. But this, in fact, really is almost the heart of the stochastic resonator, just right here. And that'll be a different video. You can also change the frequency of the noise. But that's taking a noisy signal and turning it into kind of a clean logic signal, which I guess because I can't resist, I'm going to speed it up a little bit. And we'll look at spectrum. And I'm going to do a little more time. Okay. And now we'll set it to linear. And we want the out, that's the input noise. And now here is the output. And you see this kind of relationship here, which actually we need to process more to actually get that there's a relationship here, that the noise has a certain spread of frequency and things like that. But anyway, putting noise into a Schmitt trigger is actually creating a stochastic resonator. So stay tuned.